Hello, I want to do one final problem in calculating the electric field due to a charge distribution. The problem I want to do involves a solid disk that's in the xy plane, and I want to calculate the electric field a distance d above the center of the plane and along the axis of the plane. We're going to assume that this solid disk has a uniform charge distribution to make the math easier. We'll call the charge distribution sigma, and its value is q over pi a squared, where a is the radius of the disk. So in order to calculate the electric field at this point, I have to break up this disk into small elements of charge. The elements of charge have to be sufficiently small so that the electric field has the same value over that element. So I need to break it up into a dq. I have to determine r hat, which is the unit vector that is directed from the element of charge to point P. And then I got to determine r squared, which is the square of the magnitude of the vector that is directed from the source dq to the point P. So let's start by determining our dq. We know that dq is sigma dA. We need to write an expression for dA. Since the charge density is uniform, I can actually break up this ring into rings. Not only the charge density uniform, by the way, the electric field will be the same all the way around the ring. So I'm going to choose a ring of radius r prime, and I'm choosing the r primes because I don't want to confuse it with these r's. Of radius r prime and thickness dr prime. And so this red ring that's in the drawing represents one piece that makes up the entire disk. So if I can write a general expression for my dE, and then I can sum over all the dq's, meaning I'm going to integrate my expression to get the electric field. So in order to determine my dq, I need my dA for that ring. And the way I think about it is this. Let's pretend I have a pair of scissors, and I can cut this ring out, and I somehow can magically straighten it out so that I get a strip that looks like this. The thickness of the strip is dr. The dr is exaggerated in my drawing. And then the length of it is the circumference of the red ring. And so the area is the 2 pi r times dr. So this is the element dA. This is the area of my element. And so in my expression up on top, on the board here, I put the charge density sigma times 2 pi r dr. And again, I'm going to call these r primes just so that I can tell the difference between the r primes and these r's. I get sigma times 2 pi r prime dr prime. The next thing is I want to determine the unit vector that is directed from our ring to point P. We want to find the unit vector. This unit vector is three-dimensional because we're basically doing a three-dimensional problem. But if you notice, there is symmetry in the xy plane. If I integrate around the ring, if I consider a component of the unit vector, the blue vector that we see here, a component is in the plane of the ring. If I draw the component in blue, for every component that looks like this on one side, there's an equal and opposite one on the other side. So they're all going to cancel out. So all the components in the plane of the ring will cancel out when you do the integration. I'm not going to do the integration. I'm only going to consider the component of r hat that doesn't go away when I integrate. And that component is the component that points vertically upward. So this is the r hat is the vector that points from my element of charge, dq, to point P. That's my dr hat, that dotted blue line. The y component of r hat, I'm sorry, not the y component, but the z component of r hat is determined by cosine of alpha. So it's the vector that points vertically upward here. It's the component of r hat that points vertically up here. This is one part that makes up r hat. Right. The other two components, I'll just put dotted lines, it has x and y components, but they will not contribute to the integral. And again, r hat can also be written as the vector r over its magnitude. But I'm not considering the entire vector. I'm only focusing on this term, because that's the only term that's going to survive on the integral. The last thing, or the last term I need is this r squared, which is the square of the distance from an element dq to point P. And this expression is going to be simple because for the ring, the r squared is going to be the same all the way around the ring. So this hypotenuse of the triangle is r, and r squared is the square of that hypotenuse. Again, this is the square of the magnitude of the vector that points from the source of the field to the point in which you're calculating the field. So the magnitude r is going to be the square root of r prime squared plus d squared. And so the square of this vector now I have everything I need to be able to put it together and write my dE. So the electric field due to the element of charge, this ring, is given by K as my dQ, which is 2 pi r prime dr prime. I'll divide by my r squared, and then I'll multiply by this term. But actually, I can actually rewrite this term because I know that cosine of alpha is this is d in this figure divided by the hypotenuse. So let me rewrite this term as d over the square root of r prime squared plus d squared. The next thing, once I have this, I will integrate. I will integrate from 0 to a over all such rings. But before I go on, let me rewrite this term. Zero to a, then I have k is 2 pi r prime d dr prime over, and I'm going to multiply these two together, and I have my k hat. And so all I got to do is evaluate this integral. I can do it by u sub. I'm not really interested in doing the integration. You should know how to do this already. You already had Calc 2. I'm just going to give you the answer. Yeah, and a test, I would expect you to do the U sub. But for our purposes, I'm just going to give you the final answer. And what you get, I forgot my sigma here, what you get is 2 pi k sigma, 1 minus b squared over d squared plus a squared in the 1/2 in the k-hat direction. That's it. So now you have the field. One of the fun things to do is to plot this function. Maybe plot this as a function of A. I'm sorry, as a function of D. What does this function look like as we get further and further away? Another interesting question to ask is, what happens if you're real close to the plane? What if let's say, A is much, much bigger than D? The disk will look like an infinite plane. Well, if A is much, much bigger than D, then this term will dominate over this term. This term essentially is small compared to the 1. And so my electric field will be approximately equal to 2 pi k sigma. Now, k can be written, if you remember, as 1 over 4 pi epsilon naught. The pi's cancel, and the 2's cancel. And so the field, due to a large disk or a plane, is given approximately by this expression. So when we do Gauss's law in the next chapter, we will apply Gauss's law and show that the field due to a plane is given by this expression. So this is actually going to be important for us to remember, because you're going to see this again when we do Gauss's law, when we look at the field due to a plane. Remember, if A is much, much bigger than D, if you're real close to the plane, or the disk will look like a plane. It'll look very, very, very large. Now, if you're really far away, if D is much, much bigger than A, then what you'll get is the expression for the field due to a point charge. And to be able to do that, if D is much, much bigger than A, you actually have to expand this. You'll have to factor out the D from the denominator and do a series expansion and keep the first term that's not 0 in your expansion. And you'll see you'll get the field due to a point charge. All right, that's it then.